So before we go into looking at nonlinear systems, let's first look at linear systems. I mean, one obvious reason is because they're way simpler to deal with. But of course, if that's all there is, then that wouldn't be a good motivation. We'll find out that we can learn a lot about nonlinear systems by understanding the linear system. But before we get there, let's first just review what we know about linear systems, so the basics. And the idea is that in many of these situations is that we have, say, a fixed point, meaning a solution which is time independent. And we'd be interested to know what happens in the vicinity of that solution in the phase plane or phase space. And so we could linearize around that fixed point and then look at that linearization, the dynamics in that linearization. So that's the idea. So let's consider that. So x would be the deviation from that fixed point. And so the linearization then simply gives us this equation, x equals Lx. Well, the double underscore is my matrix notation. So since L is a constant matrix, we can solve this at least formally directly. So we simply get x of t is given by e to the L t times x naught, where x naught is the initial condition. So if the matrix exponential is a little bit strange to you, let's just think about it for a moment. I mean, the exponential function is defined via a power series. So the exponential of a matrix is therefore also simply a power series. So that would be 1 plus LT plus 1/2 L squared T squared plus and so on and so on. And so now obviously we know how to operate with these things. And of course, in principle, we would have to worry about convergence and stuff like that, which we will not do here. Okay, so so we have in principle a solution, and so we'd like to know some features of that solution. And for that, of course, it's good to know that we can always transform this matrix L into a simpler form by using a similarity transformation, which in the ideal situation would lead to a diagonalization of the matrix. So we would have that if a matrix S inverse times L times S, that can be written as, I mean, you can find a matrix S such that this product here is given either just by diagonals, meaning just diagonal matrix, or slightly more complicated. So in the simplest case, right, say there would be an eigenvalue and say lambda 1 is not repeated. So there's only one eigenvalue with that value, lambda 1. And then we would have simply an element lambda 1 on the diagonal. We could have a repeated eigenvalue, maybe lambda 2 shows up twice. In general, then we know that in that case, this block could not just have a 0 here, but also this 1. So that would be a Jordan normal block, a Jordan normal form, and makes the situation a little bit more complicated. We will not focus on that right now. So let's just assume that we have simply n distinct eigenvalues, and then we have simply a diagonal matrix like that. So what can we say? Well, the important thing for what we want to do here is that, okay, the solution is given by this exponential of that matrix. And so if we have these eigenvalues, of course, with each eigenvalue, say lambda I, there's also an eigenvector, let's call it Vi, with the property that L times Vi is equal to lambda I Vi. Okay, so fine. And in terms of the exponential, we can also calculate simply what e to the LT of Vi is. So e to the LT of Vi is given by, I can scroll down, right? We still see it, so we can plug it in directly. We don't have to multiply out. So we have, this is going to be Vi plus LT Vi plus, no, not equals, plus 1/2 L squared T squared Vi and so on. And obviously, since V is an eigenvector with eigenvalue lambda, we can write this as 1 plus lambda t, t being a scalar, I can pull that out, times Vi, plus 1/2 lambda squared, t squared, plus all the remaining stuff. And we simply get e to the lambda t times Vi. And so the important thing is that if you start with an initial condition that is in the direction of this eigenvector Vi, in the linear system, the solution will always remain in that very direction. So if you think of, let's just make a little plot. So say we have a fixed point, and it has, say, two eigenvectors. This is eigenvector V1, and this is eigenvector V2. And so now what we just showed is that if initially the solution was in the direction of V1, so say it's here, then the only thing that's going to happen is that this will grow or decay exponentially. So it will, say, stay exactly in this line. And so, in other words, the space spanned by Vi, or V1 in this case, is invariant under the dynamics. The solution remains in that space for all times. So this eigenspace spanned by V1 is invariant under the dynamics. Same thing for V2, of course. The general solution, of course, is a superposition of all these guys. And so if we write down our general solution, we could write it down as x of t is equal to e to the L t times, well, we don't have to write, if I write it in terms of eigenvectors, I don't have to write it as a matrix. I can write it as e to the lambda 1t V1, and there's maybe some initial amplitude A1, plus maybe initially there's also a component in the eigendirection V2 with an amplitude V2, and that evolves then with e to the lambda 2t, and so on. So our general solution would look like that. So that's sort of the key element. So let's just fill in a couple of other aspects. Of course, the eigenvalues could be complex, in which case, since we're assuming that L, where is it? That L is real, the matrix L is real, the whole differential equation is real, so the solution has to be real. Here, L is real, and so the solution has to be real. And so even though the eigenvalues are complex, they always have to show up at a complex pair. So we would have lambda 1 equals sigma plus I omega. And the lambda 2 would be lambda 1 star, which would be sigma minus I omega, where sigma would be the growth rate and omega would be the frequency. And so the corresponding solution would be given by x of t equals some amplitude times V1, eigenvector associated with lambda 1, times e to the sigma t plus I omega t, plus, and now we know that the eigenvector associated with lambda 2 is actually complex conjugate of V1. So that's going to be V2, which is V1 star, e to the sigma t minus I omega t. And the initial conditions are real, so therefore this amplitude is also real. And so, I mean, the overall amplitude is real, and so this has to be the complex conjugate. This has to be the complex conjugate of that. And so the whole solution is real. Fine. Let me just remark, if we have degenerate eigenvalues, as in repeated eigenvalues, as I mentioned here, say if we have a Jordan block, then the dynamics are slightly more complicated. We don't have only purely exponential forms. Let's not focus on that right now. Let's postpone that till later. Okay, so what do we want to get out of this? Well, the idea is as I said, we have a fixed point. We'd like to know what happens in the vicinity of a fixed point. So in particular, we'd like to have trajectories in that phase space. So let's look at these trajectories, how they could look. So you have, let me see, start. So let's take a simple 2D example. So if we have, and let's assume our matrix diagonal. So we simply have lambda 1 and lambda 2 like that. We can almost get into this form by a similarity transform. So let's say this is our L. Then we would have, if I write now the first component as x and the second as y, I would have x of t is equal to x of 0. Let me call it x0 times e to the lambda 1t. And y of t would be y naught e to the lambda 2t. And I'd like to have a trajectory in the phase plane. And so for that, I'm interested in the shape of the trajectories here. So if I want to just scribble on here, I'm interested in what kind of shapes can these trajectories have? Do they look like this or like this or whatever? I'm just scribbling here. The point being that I'm not really necessarily interested in the time as the time here. I just want to know what shape do these trajectories have, because then I get a feeling for how this phase space, how the phase plane looks. And so I'm going to eliminate now the time from here. So I have that e to the t is equal to x of t divided by x0 to the 1 over lambda 1 power. Let me assume actually lambda 1 and lambda 2 are real, right? I mean, so okay. And I can plug that into my y equation, and I get y of t is equal to y naught times e to the t is x of t divided by x naught to the 1 over lambda 1 power. So that's just the e to the t, which I need to take to the lambda 2 power. So I have this thing here. And so I now have, if I just rewrite in a slightly nicer form. So this is y naught divided by x naught to the lambda 2 over lambda 1 power. These are just numbers, so I don't care. I'm really only interested in the dependence on x of t. And so I have here lambda 2 over lambda 1. And that's equal to y of t. Okay, so what do these things look like, these trajectories? Let's just take 2 examples. Let's assume we have, they're both positive, say. Lambda 1 is bigger than 0 and lambda 2 is maybe bigger than lambda 1. And then we would have actually y is x to a power which is bigger than 1. And so these are essentially parabolic shapes. So if this is my coordinate axis with x and y, then trajectories of this type, depending on value y naught and x naught, would be something like that. So, or another one would look like that. Would depend on initial conditions, or like that. So this would be trajectories if lambda 2 is bigger than lambda 1, and both positive means I can associate a flow direction. So I know the trajectory, let me draw that or point to it. The trajectory is this, and I know as, oh, I shouldn't point this way. This is dangerous. This is the parabolic shape of that I've calculated here. But the flow, of course, doesn't go like that because this here is a fixed point. You're not going to go through that fixed point. Instead, since lambda 2 and lambda 1 are positive, we have that x and y are actually both growing. And so if I want to make a mark, then here the flow would be like this. And if x had been negative, the flow would be going to the left with y growing. So the point is we have a flow like that. And if they had opposite signs, we would have simply, I shouldn't say simply, if lambda 1 was positive, lambda 2 was negative, then this would be y would be x to a negative power. And so those would be hyperbolic shapes. And you would get orbits or trajectories that look like that. And again, if I want to put arrows on there to show which way the flow goes, lambda 1 is positive, so the x increases, lambda 2 is negative, y decreases indeed, right? So these would be the flows. Okay. So this already gives us a good idea of what kind of things can happen in the vicinity of a fixed point. I just want to add one more feature, which is essentially just a bunch of definitions. Let me go back. We had that if you start with an initial condition in one of those eigenspaces, the solution remains in that eigenspace for all times. So we have these invariant subspaces, and so in principle, each eigenspace for each eigenvalue is an invariant subspace. But what we are usually really interested in is mostly, well, this fixed point, it could be stable or unstable. And if it's, let's say this one, it's stable or unstable, well, the flow is going down in the y direction. So it's stable in this direction, but it's unstable in this direction because its x is going out. And so that's the information that's really important. And so what we really want to discriminate are between the eigenspaces with a positive eigenvalue and those with a negative eigenvalue. Or more precisely, positive and negative real part of the eigenvalue, if it's complex. And so one defines these eigenspaces the stable eigenspace, let me write down. So the stable eigenspace is essentially spanned by all the eigenvectors that have a positive eigenvalue, positive real part of the eigenvalue. So the stable eigenspace, well, the way to really formulate it would be all the vectors in Rn, if our system lives in Rn. And well, as I said, we think of this as all those vectors V that, wrong, all those vectors V that have a certain eigenvalue. So so if V is an eigenvector with eigenvalue lambda, then this would be 0. And so this would be, if lambda was a single non-repeated eigenvalue, this would be a one-dimensional space. But in general, since we're not talking about the stable eigenspace, so we want to have actually all eigenvalues in here that have a positive real part, stable, negative real part, where lambda, the real part of lambda, is actually negative. So now this is a large space, possibly, because there may be many negative eigenvalues. Also, just for completeness, so to speak, the eigenvalue could be repeated, in which case, actually, you also have to pay attention to the the generalized eigenvectors. And so, say if it's m times repeated, this is actually the L minus lambda to the mth power. So if, maybe I should write that down precisely here. If lambda is m times repeated, you can check that this does exactly what it should do. It's not a hard calculation. I'm not going to do it now, but you can check it. And similarly, you would define the unstable eigenspace are those V's that satisfy L minus lambda to the mth power V equals 0, with the real part of lambda being positive if lambda is m times repeated. In the notes, I also write out the definition. If you have a complex eigenvalue, then you would make that space a little bit, define that a little bit differently. That's sort of a technicality. The important thing here is simply just that we introduce the notion of a stable eigenspace and an unstable eigenspace. And we'll use them later when we go to the nonlinear system in various ways. You notice that there's no case here where lambda is actually equal 0 or the real part is equal to 0. That would be the center eigenspace, and we should actually also define it, which will play a very important role later. So let's just define it right now. V equals 0, and lambda is the real part of lambda is equal to 0. Okay, good. So now we're equipped with looking at typical face portraits in 2D. That's where it's easy, and we'll do that next time. So, but this is already essentially was a review of what we know about linear systems and what we need for our nonlinear analysis when we then take this as the linearization of our nonlinear system.